All right, thank you, everyone. Can you hear me okay in the back without a mic? Yeah? Okay. That's what that's for. All right. So today, my intent is to give a little bit of idea as to how Netflix has applied reactive programming over the last couple of years in the edge systems where I work, and then give some kind of insight into how we've been thinking about what we would do if we did greenfield, like started from scratch again, and what it would look like for us to go fully reactive, and then tell you a little bit as to where we're going in the future in the edge systems engineering, and what that means for RxJava, RxJS, and some of the other libraries that we're using. And if you're wondering what on earth edge engineering is all about, edge engineering is it's the group of teams at Netflix that manages all the incoming traffic from devices and UIs. So it's the service gateway, it's the public APIs, it's the routing tier, it's all those different teams that build and operate all of the traffic that powers all the devices out there. But it does not represent any of the actual business functionality. It's all in the middle tier. Those are all the things that we end up depending upon. So it'd be great if we could always just start from scratch and do a greenfield development, but it's incredibly rare. More likely, we think that our applications look something like this. Generally, this is how engineers think of software, that we feel it's decrepit and old and not so great. More likely, though, it's like New York City, which is actually very sophisticated, very mature, and is getting the job done. But you've got the equivalent of decades worth of different times of building, fitting things differently together. You've got some new roads, some old roads. You've got some nice new plumbing, some ancient plumbing. And this is generally the reality of any successful system, because it's incredibly rare that a system got successful right after it was greenfield. Generally, you've been through a lot of iterations. We all want something that looks a little bit more like this. I have actually never seen one of these. So if you're aware of a software system out there that is representative of this image as opposed to the previous picture, I'd love to see it. But our goal at Netflix a few years ago was to try and take a few of these things and try and bring it back into the New York City picture, get it a little bit closer. And it actually was a very simple problem we were trying to solve. We were trying to take single incoming calls and do a lot of things concurrently. And the reason why we were trying for that is several years ago we noticed that the device traffic coming in that was based upon the typical RESTful model was very fine-grained and incredibly chatty. Any one request coming in would hit one thing on the back end typically. It was actually like 2 or 3. It would do like auth, get some user data, and then do the one thing it did. So for every one thing you did, you actually had attacks of 2 other things. And that was how all traffic in the front door behaved. And we wanted to do something a little bit more like this, where I could come in a little bit more coarse-grained and go and do 8 or 9 or 10 things and better utilize the latency round trip over the public internet. And we realized along the way that we needed to embrace asynchrony and probably something along the lines of callbacks. And the 3 things that meant for us as we were figuring out how to solve that is we needed to do service composition. That was actually what we were looking for. We weren't looking to be async, just be async. We actually needed to compose the responses and the behavior of multiple different services, microservices if you want to use that term, but services. And while doing so, we had to take into account error handling. I couldn't just have things blowing up all over the place. And in asynchrony, oftentimes error handling can be challenging. And then developer productivity had to be taken into account. We couldn't just ignore that aspect and say, we're going to solve this, but in some crazy hard way that all of you are going to have to go through some like arcane training and you're going to lose, everything's going to take twice as long to develop. That we couldn't have that be the answer. And it didn't take long for us to realize that callbacks was not at all what we wanted to do. All you have to do is go Google anything about callbacks, and it almost always ends up at callback hell. There's literally websites called callback hell. And we didn't want that. So we wanted something more along the lines of futures. And futures, as long as you're not using Java futures pre-Java 8, they actually are pretty great. Java futures, which is where we were at circa 4 years ago, they suck. They don't even deserve to be classified in the same space as what we're talking about here. I'm not going to go into all the different types of futures out there. Scala's got great ones, Twitter's got great ones, Guava's got a decent one. Java 8 finally got involved, got in the game with completable future. It's good. It's a little odd in some of its design, but it functions. The thing that was unique in what we were, I don't know if it's unique or not, but it was clear for us is we actually have a lot of cases where it was an asynchronous request for a list of something. And that became quite common in our patterns. And so for us, an incredibly common pattern is you get a list of movies, and then for each list, and then within that list, for each movie, you go and fetch a bunch of stuff. And so we wanted to have a model that could not just model the request response semantics, but also model the iteration of the data that we were receiving. And this last one, it's generally not a good way to do it with futures, but it's a future of list of futures is actually semantically kind of what we were going for. We wanted to be able to asynchronously fetch something that would then asynchronously send the data back to us. And so all three of those actually get represented by the stream type that concretely in Rx, in reactive extensions, is called the observable. And effectively, this led us to a point where we treated everything as a stream. Everything that we modeled as far as our interactions with services became a stream in how we thought about it and how we modeled it and coded it, wrote the code. So instead of me using Netflix things like I often do, I'm using orders and products and shipping status instead, because virtually everybody has at some point messed around with a system like that. And so in a synchronous world, these three things would have APIs where you invoke them and you sit there and block, and you get back lists of items or a single item. And this is the typical blocking API that most of us have written for a very long time. And most of our code bases, I imagine for most of you, they still look like this. And it's a lot easier that way, actually, because it's how we think. You request something and it comes back to you. However, the behavior of this is that you typically step through each item one at a time. And when you're dealing with I/O over a network boundary, that typically is time that is wasted, and it starts to pile up and affect two things. Your user experience latency, so the perceived time for them to get a response back. And it also typically, the way that most of our systems work, means that you're really using your infrastructure inefficiently. So the reality for us, though, was that almost everything we talked to was synchronous I/O like this. So we were doing inter-process communication, RPC, over Apache HTTP. We were hitting Memcache D systems. And ironically, even though Memcache is phenomenally good at providing you async approaches to talking to them, all of our clients were synchronous, just because that's how they had all been modeled. Cassandra was all synchronous, blocking I/O to them. And we were using Tomcat and servlets everywhere. Like, that was just the way that everything was done. So every single one of those is blocking. And so the question for us is, what on earth are we going to do within that worldview to achieve some of these things we were trying to do with async? And so the reality for us is that we actually couldn't change a lot of the ecosystem we had. Like, there was no way on earth that we could say, we would like to improve a little bit over here, so we need to rewrite Netflix. Like, that just wasn't an option. Not only would it have just been laughed at, and we would have been, like people would have questioned our sanity, it would have taken multiple years and probably would have destroyed the company in the meantime. And so we needed to look at what we could change. What we could change was the service layer. The abstraction on top of all of those things was within our control. And so we chose to leverage the fact that that was fully in our control and start to decouple ourselves from the choices and architectural things that we couldn't touch. Now, that's not the most efficient way to solve all these problems, but it was far more pragmatic. And this is what I'm going to start talking to you about now is effectively how the Netflix Edge systems have been running for the last 3-ish years in this like mixed mode of part of it async and reactive, and the other half of it, all those synchronous things that still exist across most of the company, and how we kind of pulled those two together to achieve what we wanted to do without doing the impossible or just giving up. So we created an async facade on top of a synchronous infrastructure. And the two blue blocks here are the pieces that are all synchronous and they all stay the same. So the one on top represents that we were still living within Tomcat and we were still living within servlets, which is all blocking I/O and thread per request. And at the bottom of it, the big blue one at the bottom represented all of the dependencies that we needed to talk to. And for a variety of reasons, the client libraries were not something we could go and change anytime soon. And so we just had to deal with the fact that they were all going to be blocking synchronous I/O for a good long while. So we went about changing that. And the question is how do you get from the top piece to the bottom? And so we wanted to go from everything being synchronous APIs, like get orders, to having like a get orders async. We didn't call them that, but that's what we wanted to do. And so we went through our entire service layer and we rewrote it from the ground up with everything as observable APIs. We didn't leave a single method in there that was synchronous and blocking. Every single one became an observable API. And that meant that we started to write code that looked more like this. We would have an async method that we would invoke that would then get composed within another async method call that all gets composed into an async stream. My goal right now is not to walk you through what flat map and those types of things mean. Due to the variety of things I'm trying to communicate today, either you understand flat map or just park that on the side, come up and harass me afterwards, and I can point you to some places that explain what flat map is. Because the first time I experienced flat map, I had no bloody clue what was going on. So don't worry if that's you right now. But just think of these things all being composed together, and it kicks it all off asynchronously, and it all happens in unicorns and happiness. The difference here is that it all just happens. And so if I do that again, that same example from before, this time it kicks off and then it all snaps into place because it fanned it out and it allowed everything to happen asynchronously. It fetched all that data, and instead of it stepping through each one at a time, it allowed them all to happen concurrently, composes them all back together, and it hasn't changed actually the amount of work I've done at all, but it has changed the perceived latency for the user because I leveraged parallelism to go out and pull these all back, whether it's happening on multiple threads or an event loop or whatever is orthogonal to this. It's all about the perception to the user. So how do we get from a blocking API to a non-blocking one? And that's what I'm going to spend the next little bit showing some of the very practical ways that you can take something blocking and turn it into non-blocking, particularly when you can't change the underlying infrastructure. Because that's one of the biggest issues that I hear people often talk to me about, which is, hey, all this is great and fancy and wonderful, but the reality is I got JDBC in my system and that database isn't going away, or whatever it is. So I'm going to talk through some of the ways that you can bridge those. So one of the most simple ways is you literally just wrap the API. And so in this case, I'm going to be using the RxJava syntax here for this. And defer is a mechanism literally for just saying, when this is lazily execute later, you're going to run the code that's inside here. And inside there, I'm literally going to go and execute that blocking call and just return whatever it gives me. And then that would all be quite useless if I don't actually make it execute asynchronously. So I inject concurrency by running it off on an I/O scheduler. And so in RxJava, anytime concurrency is going to be added, it's parameterized, which means that it can always be injected through methods and overloads. And a scheduler, you can think of it in Java land as like an executor service. except it's raised up a level so that we take control of time, and we can control things like thread affinity, so that all the events coming through will all stay on one event loop. Things that executors do a miserable job at, we use those under the covers and make sure that they maintain the contracts of streams, so that everything, one stream stays sequential, for example. But what it means is that you can choose which threads you want to put anything on. And so the I/O scheduler literally is just an unbounded thread pool that will allow you to block something on there because you're blocking I/O over there. We also have computation schedulers, which is a pool of event loops. If you're doing anything non-blocking, you can put a new thread on. You can run it whatever you want. Question? Yeah. Are schedulers responsible for backpressure if they're using the sequentialness? Schedulers, no. Schedulers are completely outside of backpressure. They'll literally just queue up whatever you put on them. Backpressure is the responsibility of the stream itself and the operators. So this get shipping status, you'll notice in this example, we didn't actually change that. So this is an example of, I've been given a third-party client library that I have to use, and I don't yet have the ability to influence them to change. I just got to deal with it. And this is a way of doing it, and this is how we did most of it for years, because trying to convince everybody to change just for us wasn't going to happen. Now, any of you who have dealt with system efficiency are just like, kind of squirming right now, going like, really? You're just like wrapping everything in threads? It's like, yeah, actually, that's what we did. And what we found, I'll get to it later, it definitely has a cost and overhead, but because of what we were dealing with here is the perceived user latency on things measuring tens or hundreds of milliseconds. And so the overhead of adding extra thread scheduling events and those things was worth the cost for what we were aiming for. Yeah. If you were to do it again, how would you implement it, or would this be the way? It would be very similar to this. So the question, if any of you didn't hear, is if we were to do it again, would we change anything about how we did it? There's one area that I would dramatically do differently. It was a really dumb mistake that we've been paying for ever since. And it was actually, I'll get to it in a little bit, but it was the layer at how we hooked into the Tomcat servlets. The actual wrapping of background stuff, there's only a few ways you can do it. It always ends up being wrapping it with a thread somehow. And so that has never been the problem for us. We ended up with about 3 different ways that we do it, just in different places that were a little bit more appropriate. And we've been pretty happy with all of them. In reality, though, we actually don't do what I just showed you, because we do something a little bit more complicated. For fault, we use Hystrix for all that stuff, actually. So Hystrix is our fault tolerance library and bulkheading. And along for the ride comes concurrency and metrics and insights and bulkheading and circuit breakers. And so we actually leverage that across all of our systems to both make them async and provide fault tolerance. So what does it look like if we have a method that actually returns multiple things, which is quite common for us? In this case, it's also modeled as an observable. And the only difference, it all looks the same, except that instead of saying just one item, you can just do from. Now, the observable representation here is not nearly as valuable as it could be if you actually had a true stream, because all it's actually doing under the covers is it's going to still get back one thing in one response and then just turn it into a stream and iterate it out. And so from an efficiency perspective, we're actually not buying ourselves much. But what it does buy us is the programming model, and so that over time, as we change things, the abstraction in how we program against it is it's representing how the data actually is correctly. And then under the covers, we can change out whether it's streaming or batch or however we do it. And it also means that when you start to compose things together, it's honest about the data type you're dealing with. I can compose a stream and then for each item go and compose against all the other things. But for any of you who are wondering, like, is this really benefiting from how you stream data? No, it's not. We're still fetching it all as one batch, request response, and then just turning it into a stream in memory. So this is the simplest possible way of bridging from blocking to non-blocking, is we literally just wrap them with threads. So what about JDBC? So JDBC, you have this get orders method, and you got all this code. Now, one way we could do it is before you just let it all happen, and then you do the from on it. However, if you can get inside and re-implement that getOrders method, all of a sudden you can start to take advantage of true streaming responses. And so this, I'm now assuming that you can edit or refactor or add a new method to that previous method so that you've convinced that team who gave you that third-party library, or it's your own and you're using JDBC. So right here, this is the way that you're returning a list of orders that you've accumulated. All right? That's not the most efficient way to do it. If instead I return an observable instead of a list, now I create an observable and I do all the same blocking code inside, except now inside my while loop, I'm on-nexting out the stream as I'm getting the data from the database, rather than accumulating it into a data structure and then returning that data structure at the end. So now I'm one step further towards representing the data as it truly exists. And I'm also not allocating memory in these bursts. And so one of the things that you see in systems a lot when you profile them is that we literally, like, in a function, you allocate this huge amount of data, you pass it over, and then you turn it into something else, you throw that away, and you just keep allocating and reclaiming along the way. The observable approach, you never allocate any of that memory because it's just a pipeline that just shoves it down and you just process each item as it comes through. And so it's much better for like GC pressure and those types of things. The error handling and completion. Error handling is important. So this is one of the first places where I've demonstrated how the error handling is done. So the terminal event on any stream is either an onComplete or an on-error. So on-error, you can think of it anytime you're going to throw in imperative code. On-error is the way. And errors are just events. They're just an event on a stream, but they're special in that they will terminate the stream. You can't have anything happen after an error. And you'll also see here this is unsubscribed. And so any stream is capable of canceling early. And so this is the part where, because we're in an imperative block of code here, where it's checking effectively the cancellation token as you're going around it. If you didn't have that and you canceled, you'd walk away, but it would still be off running in the background. And so this is the way to be efficient. Now, this is going to be the most complicated piece of code I show today. I wanted to show at least how you can get the backpressure stuff in there if you want, because that previous example I just gave, absolutely no backpressure whatsoever. That will fire hose the data at you, and you have to be ready for it or not. And if you have queues in the way, either they're going to be unbounded or they will blow up if they're bounded. So if you want to get the backpressure approach, I'm going to use a generator function to make it a little bit simpler, because if you do it from scratch, it's painful. And so this abstract onSubscribe at the top is going to give us kind of a state machine to help us out. So I create this thing, and the first thing that happens is I want to have a state object of the result set. And so when this thing is invoked, when it's subscribed to, the first thing it does is it executes this lambda, which initializes the state. And that state is, I'm going to get the database connection. I'm going to create the statement. And then this is for MySQL code here. It's the mechanism for, you set the fetch size and these arguments for type forward only and everything. What that does is it's actually telling the MySQL driver to stream results, because I think it still is the default that it actually batches everything up, which isn't what we want to do. So this is telling it to stream the results down the connection rather than batching them. And then I actually execute the query. And so I'm doing a really stupid query here. The select star from orders. And so if there's like 10 million of these things, the thing is this actually could work because you're a streaming model and will support cancellation. And so it will not blow everything into memory at any point in time. It will just stream them through. The next lambda here is this will be invoked at the rate of which the consumer can drain it. And so this is the point where RxJava and the reactive streams model, they kind of support this push-pull back and forth. So as long as the consumer is fast enough, this will execute as fast as it can possibly go and just keep on pushing. If at any point in time the consumer is slower than the producer, this will stop executing and it will effectively turn itself into something like a batch iterable or an async enumerable, and then it will only run whenever the consumer requests more. And so in this case, what it does is it grabs the state, which contains the result set in it, and then it does the next. It moves it forward one, grabs the result, on next it down, or completes as it needs to. And because this state machine takes care of this for us, if anyone cancels, we close the connection, and that will get invoked either on cancellation or on termination of the stream. And then I just ignored, for brevity on the slide, some of the try-catch stuff. And then again, because JDBC is still blocking, I need to move all this off onto an I/O scheduler because I need it running in the background because it will block. So we end up using basically these mechanisms from Observable to allow us to bridge from blocking code to non-blocking. And it goes from very simple, just wrapping of a method, up to the much more advanced example I just showed you, and everything in between. So that's about how we wrapped the bottom part here. So the async facade down to the blocking, all the blocking calls underneath. But what about the top layer? If I have to still live within a servlet world or a blocking I/O thread per request world, you end up generally with code that looks like this. So this do get, for anyone who's done servlets, you'll be familiar with this. You get the servlet request and response, and it's a void method, and it expects everything to be synchronous and blocking. If you just asynchronously do stuff and like walk away from this, it doesn't work. The response will never get back to the customer. It will close the connection. Just bad things happen. So how do we mix the two? Well, I have to deal with these blocking calls, but I still want to perform all my composition asynchronously. So I'm not getting any efficiency gains like event loops or anything like that. I'm still a thread per request. But when that request comes in, I'm going to fan out and do all of my work on multiple threads. So in this case, it's that code I showed earlier. I go off and get shipping status. It returns an observable. It's getting the orders asynchronously. For each order, I get all the products. And for each product, I get the shipping status. So this is potentially a very large fan out, and it's going to happen all asynchronously. When it comes back onto the servlet thread, though, it kicks all that off. And then I say to blocking, which we explicitly name that way in Rx so that you know that you are blocking now. We didn't want to have like any, like it's just for each or something like that. We very explicitly, like you see that in your code, you are blocking the thread. Like behind the scenes, that's a countdown latch. We are literally just parking the thread right there. And then we turn it into the equivalent of a Java 8 stream, which is not async or push, despite its name, or an iterable with higher order functions. And we iterate over the responses, the output, and we write them out synchronously on the blocking I/O response for the servlet. Okay? And then because we've moved back into blocking, it will throw exceptions. And so you're back into imperative synchronous world. And so what we've done is we've wrapped all the imperative stuff around this block of async, and we bridge back and forth between them. And so what we've done right there is we've mixed the two worlds. We're within a blocking system, but we're fanning out all of the code, all the I/O requests to do the work concurrently. Now, previously I had mentioned that there was one thing that I would have changed dramatically if I could go back in time. So our system is way more complicated than this. We actually have a layer of Groovy on top that all the different user interface teams can write their own code dynamically and deploy into our system. They write their own web service endpoints for each device. And I made a really stupid mistake. I gave them the actual request and response references and gave them full control of the subscription lifecycle of the observable. And that completely has completely handcuffed us ever since to fix all kinds of issues. If I could go back in time, it would have saved us so much grief. I would have instead just had them do a function that declared an observable and gave it back to us, and that we control the subscription of that observable and hooking it into the I/O. That has caused so much grief that that's the one thing in the last 3 years that I wish I could change. Otherwise, all the other integration points have been quite good. That's the one thing. If you're doing observables like this, users of the system should never call subscribe. It should be like it all gets composed together, and then the system at some point says go, and it subscribes to the whole thing, and it's just all composed together. Because whoever controls that final subscribe controls the full life cycle of everything that's going on. So to blocking, this is the bridge between async and sync. And its most common use is actually in unit tests and demo code, when you're like throwing something up on a just so you can show someone how to do something. That's its most common use, because you just need to block the main thread, otherwise like Java just shuts itself down. But it can be used in production systems if you know what you're doing. Just don't use it on an event loop. Okay, just don't do that. That would defeat the whole point. So how did it go? We added this to an existing code base, and how did it go? This is a really important question. So it took us 3 tries the first attempt. We were actually building the Apple TV endpoints. The first 2 were definite throwaways. They sucked. The third one still sucked, but it worked. And there's 3 or 4 of us involved in those first like 2 months, and this is kind of how we felt the whole time. Like, what the hell are we doing? Like, why are we putting ourselves through this? Because if like I take myself back in time, all of us, we had just been doing imperative programming for like our entire careers, like this whole like functional thing off on the side. A little bit like our async experience was like, yeah, I'll like throw something in an executor service and get a future back and then block on it, right? So what we found is that the tech worked. So the RX, and that's not because of us. That's because Eric Meyer, who invented this stuff over at Microsoft, his tech worked, and our implementation of it worked. We were still figuring out what it all meant. So we learned some things, not quite at that point, but over time as we matured. So first of all, we had to relearn a lot of our idiomatic approaches to how to solve things. A lot of the things that we just took for granted over the 10, 15 years most of us have been coding, we had to like unlearn those and relearn new things. So an example is, if you have some iterables or arrays or whatever, and you iterate over it, you stop doing that. There's no such thing when you're doing async. Instead, you map over something, or you apply functions to this stream that just kind of happens underneath you. And so you're like inverting the model, and this took some time to get used to. Another one is try catch. Some really interesting code over time. As people were in between phases and they were learning, they'd write all this async code, and then they put try catch blocks all around it and be like, so it's not working. Like, what's going on? Like, because that method like was done like 5 seconds ago. You're over here now. You're never going to throw an exception over there. It's all async, right? And so to learn that you have to like start to do your error handling as it's an event through the stream. Try catch, totally useless on the outside of a stream. Within a user function, that's fine. So this is another one of those things that because we're working within a language and a runtime that was never meant for this, we had to you have to pay attention to what the hell you're doing with a try catch. The other thing is we had to invest in documentation, and documentation was hugely important for what we were doing because it was all new to all of us. And so not only did we spend the time on the Java docs, but we did it on wikis, and we had tutorials. We actually paid for a tech writer, and we've had him for the last 3 years on the project. And so we actually invested money in it, not just developer time, but money to get a proper tech writer, which made a huge difference in the quality of the docs. And even as we moved it into open source, he stuck with it, and it's pretty awesome. If you're going to do open source, do it this way. You commit code, and then he sweeps in after the fact and commits all the Java docs after. Awesome. So, and like the diagrams, there was an engineer on one of the teams I work with who one day is like, we should do these. So like, I literally was walking through the office one day, and like I saw these like printouts, like cheat sheets, like when you study with like flashcards. They had like the 10 or 12 first operators, like flat map, like how does this work? I'm like, who did those? And it was this guy George. And so I'm like, whatever you're doing, we need more of that, but like put it up on the site. And then that became a thing. And now like every single operator has these things done as diagrams to help visualize what's going on. And eventually, over time, it matured into a website and lots of documentation. Then the community got involved. Documentation has been key. And we also found we just had to allow for time and mistakes for people. My experience is that it takes an engineer who, and by engineer, I mean someone who's been around like 10 plus years of development. So they already know code and systems and operations and all that stuff. And they're moving into this new model, 2 to 3 months. About 2 to 3 months for them to truly get it. Not just so that they can like hack something together, but so that they like have that aha moment and they've changed their thinking and they're like legitimately able to code it and debug it. If you can't debug the code, then you don't get it yet. Unit testing and debugging have been, these are important areas to understand too. So first, unit testing. Async unit tests, not nearly as hard as it would seem. So here's an example of an observable, and this one is asynchronous. The way I can tell it's async is that it's doing this interval thing with time. So anytime you have one of those in Rx, it actually has an overload that I can pass in a scheduler, and I'll show that to you in a second. This one, implicitly under the covers, is using the computation scheduler. So if I subscribe to that, my unit test will just complete. Okay? It'll just complete and it won't even finish. At the bottom, at the top, sorry, this test subscriber comes right with Rx as a first-class citizen for helping you do testing. And you subscribe to the test subscriber, and then the test subscriber gives you helper methods like awaiting a terminal event. It does the countdown latches and all that stuff for you, so it blocks the JUnit thread, and then it allows you to do the assertions of what you've received. And so that you can have async code that runs and then do all the synchronous blocking stuff. It gets far more interesting than that, though, when you're testing things with asynchrony and time. This test subscriber, seen that, you subscribe with that, but this test scheduler, this is where it gets really interesting what you can do. Something that's really challenging when you're dealing with time in unit tests is it's completely non-deterministic. So I actually spent 3 hours this morning trying to deal with some stupid race condition in code that I haven't figured out yet. It's because on my laptop, it works beautifully. My code's awesome on my laptop. When it hits Travis CI, all hell breaks loose. Like the tests are just failing all over the place. So I've got some race condition somewhere. This helps with that stuff because this test scheduler actually does no concurrency whatsoever. So I pass it into the interval, which needs time, and now I actually get to deterministically and artificially advance time as I want to. So I advance time by 200 milliseconds. I know guaranteed, whether that took 1 millisecond or 2 seconds on a given machine, that I will have emitted only 1 tick from the interval. And I keep advancing the time, and now I can see that I've received the 5 values out after 1 second. Totally deterministic. This allows you to take something that has time involved and generally concurrency and make it all single-threaded and deterministic. You can use your debugger to walk through it. Like everything about it all of a sudden becomes synchronous. And then you flip it back into production with real concurrency, and it all just behaves like you would expect with all the normal race conditions and all that stuff. So that's incredibly useful. Async debugging, though, is still hard, and it sucks. Running on platforms that were never built for this, like the JVM, their stack traces have no idea what to do with this kind of code. So lambdas, sorry, go back. Oh no. I don't know if any of you have done Java 8 stuff yet. I love lambdas, but they make stack traces just ridiculously bad, so that doesn't help. And then you end up with, like, whenever you schedule something asynchronously, like it completely loses the stack trace. We have spent inordinate amounts of time figuring out how to stitch call stacks together. To do it in any sane way, it destroys your performance by like orders of magnitude. And all the insane ways to do it that even come close to performant are just like you're dealing with like C and assembly inside the JVM guts. And like thus far, we have not yet found one that is worth us doing in production. This is something, like I know that TypeSafe has been doing some stuff in this space. I would love for Oracle just to solve this one for us. This sucks. So be ready for that. And also the stack pollution. There's just really no good way for this. Takipi is a startup that's working in this space, trying to solve some of these things. We've spent some time talking to them. There's a lot of work to do in this space of making stacks better and stack traces in async useful. RxJava does try by putting in certain error messages that are useful, but it can only do so much with what it's got. Debugging, stepping through in async, I mean, it's no different than if you're using futures and thread pools. Just when you're using Rx, you've got lambdas and like these sequences and all that stuff, step-by-step debugging is pretty useless. You never actually step through what you want to step through because it has no idea what you're doing because it's not imperative. So you set these breakpoints, you'll never actually end up where you want to end up. So this is a problem. Async code, you just don't use debuggers very often. You end up doing that. So it's not happy, and like the race condition I was debugging this morning, I got lots of print lines through my code base right now. So this is a reality of going async, and an even greater reality of async plus functional composition. And if you're thinking otherwise, like, don't be scarred when you get there and realize that this is what it's like. And yes, that is the state of the art. So async debugging is hard and it's a work in progress. I'm hopeful that as companies like Takipi and TypeSafe and others focus on this and invest money in tooling, it will get better. Like I know that TypeSafe with Scala has been doing some stuff recently on the tooling and IDs in that space. So I hope that that becomes much more widespread as time passes. So how about once it's all done? So these observable APIs worked well. And we were able to go from call patterns like at the top, where you had lots and lots and lots of very fine-grained calls, to one like at the bottom, where you'd have one coarse grain that did everything concurrently in the background, on the back end, much more efficiently. We removed a lot of the redundant stuff that we didn't have to do every time. And that all worked really well. We replaced the blocking APIs with observable APIs. And the layering of our system looked something like this. Along the top, this is all of our clients and devices out in the field. So this is like your PlayStation or your TV or whatever. And the majority of those run JavaScript for the UI layer and C for so it's got C in the bottom and then JavaScript on top. And most of them use RxJS to do all the function composition and asynchrony. Then even now, we're still using synchronous HTTP. In a little bit, I'll tell you where we're headed with that, but it's still synchronous HTTP. And then the Groovy layer, we use RxGroovy. And then the observable APIs in RxJava. And then all those porcupines along the bottom, that's the Hystrix layer. And we use that to bulkhead and isolate all of our backends that we talk to. And that's also what gives us our concurrency and asynchrony. They're all pushed off into their own independent thread pools for concurrency reasons, but also primarily for fault tolerance, is why we had those thread pools before actually we wanted concurrency. We did that for bulkheading reasons. So definitely challenges mixing approaches. When you've got these two different ways of doing things in the same system, it's really easy to like all of a sudden have something that was nice and concurrent, all of a sudden all becomes sequential again. It's really easy to get confused as to what's going on. Like honestly, we have like over 1,000 threads in that particular system. It's kind of insane. So too many threads. It's hard to tune and shed load when you have a system that complicated and that like mixing patterns like that. So that's a reality we've had to deal with. It's really easy to accidentally block async code for two reasons. One, because you've got like a huge chunk of your code base that's still blocking that you can accidentally invoke. But also because we're working in a runtime and a JDK, it's APIs, where it's all intended to be blocking. And so you gotta like be careful about what you're doing. Here's just one example. This one at the top is concurrent, this one is sequential, and the only difference between them is really it's 4 characters in the method you're invoking. So the map and flat map, if you don't actually get and grok what's going on here, it's really easy for someone to say, I'm just gonna map over it at the bottom and call the blocking get shipping status. But you just made the entire thing sequential. You just defeated the entire point of doing this, and you shouldn't even be using this style of coding. So what we did to help solve that is we just made it so that we don't have any blocking calls in our API. So in the layer of the API that you should be working with, we just got rid of them all. Now, because there's no modular system in Java 8 and earlier, there's no way for us to prevent someone from going off to something else and touching it. But at least we made it so that within the API space that they should be in, we didn't have blocking and non-blocking calls sitting next to each other so that you couldn't just fat finger it, autocomplete into screwing yourself over. And so everything was observable, and so we tried to avoid that case. So this has led us over time to the question as to should we go fully reactive? As we explored that, it was all dragons out there. It's like myths and legends and things like, well, yeah, it's because it's better. Totally, it's better. The best way I got this, I'm not going to name the company, but there was a company who had just went fully to Netty, and they went fully non-blocking. And so I went over there one day and started asking him about, like, walk me through it. And at the end, I'm like, so why'd you do this? Like, that's a lot of work. Why'd you do it? Because it's better. Like, but like, what performance gains did you get? Like, was it more efficient? Like, we're not really sure. I'm like, what the hell? Like, that's not an answer. That's not engineering. So, because it's better is not a legit answer. And then there's also this. Like, if you Google any of this stuff, like this, you'll get it's worse equally as often as it's better. And so that's not helping the cause. This is actually almost the answer. It really doesn't matter what you do. And you start digging more and more, and you get like all these things. And my conclusion is that theoretically, it doesn't matter what you do. They're actually all equivalent depending upon the implementation. Because at the end of the day, it actually is all just scheduling things at assembly somewhere onto a silicon or my CPU. And if I could have a threading model that works better, like a blocking threading model that works better than a reactive model with like event loops and stuff, if I implemented them correctly. And if you start to look at like the C10K, C100K, and even now C1 million, which is about like like how many connections you can have on a box, this is the only place I was able to find anybody who actually agreed that you had to go like non-blocking to achieve this. Otherwise, they're like, unless you're doing that, it doesn't matter. So this is a really hard thing for us to say, like, well, what are we going to bet the future on? And where are we building towards? And we didn't want it to be myths and legends and like different opinions and stuff like that. So, we did the worst thing you could do. We went and tried to do a benchmark, which is disaster. So we wrote up a test that basically simulated the type of stuff we do. You kick off two things in parallel, and then that one does some more work, and then some other work, and it all comes back, and it takes about 154 milliseconds for all this to happen. Like that's the fastest it could possibly be. Now, starting down a path of this kind of thing, you get it wrong, guaranteed. It took us over 6 months to actually have data that I actually trusted. And the only reason I feel like our numbers are even remotely meaningful is because we had the chance to work with Brendan Gregg, who has written a book this thick on system performance. And the guy has forgotten more about computers than I will ever know in my life. And so I had I was lucky enough that I got to work with him on this. And it was fascinating to watch him do his thing. Like, he would like warm up the machines and let them run for a few days to like get the jitter out of the systems before he would like actually trust that the data on them was legit. He got a patch into Java 8 update 60 so he could attach profilers to it. So like, this guy's legit. So as we went through it, we tested on this. We were testing Netty and Tomcat because that's what we were looking at. So these numbers are only representative of the worldview we were trying to do, but they helped us a lot, and they actually do teach us some things. So this is telling us that our load test is actually saturating both of them. That we were pushing both of them to near 100% CPU usage. A load test that does not do that is a totally useless thing, because then you're not comparing the same things. This is where it starts to show what's going on. So Netty has lower CPU consumption. The red, per request, it was taking less time than Tomcat per request. Now, that actually doesn't mean anything about architecture. That could just all be that its code is better, which actually is true. Okay? Now, this one, though, the throughput, Netty starts to trounce Tomcat as you push it, okay? So the RPS is able to get way better. Now, this is just, again, because the CPU consumption per request on Netty is so much lower than Tomcat. So again, we actually haven't proven anything about the architecture yet, just that Norman and those guys write really good code. So the theoretical best possible time over there on the left is 154 milliseconds. And you can actually see at low concurrency, the two of them are pretty close to each other. The Tomcat's a little bit worse, again, just because it's not as good, the code is not as good as Netty. But you start to see that as you hit the right side, there definitely is a difference. And it's really severe when you look at the max latency. So this is average latency. Average latency is totally a useless thing. And I put it up here actually on purpose. Because if you're just looking at average, you don't know anything about your system. Okay, so because I'm not trying to take the entire night, I'm not showing you like every single percentile along the way. So I'm just going to go to the max latency. And the max latency, you can see that it just goes all over the map. Like you go from 900-ish milliseconds up to 2200 milliseconds. So what's going on? So the CPU instructions per cycle, pay attention here that Netty is actually doing more work per cycle as you get higher under load. The first time I saw that, I didn't understand at all what was going on. Like, it's actually getting more efficient the hotter it gets. And when you start to look at what's going on with threads, you really start to see what's going on. So remember that Tomcat is a thread per request, and Netty is running on event loops. And so you can see that when the system is not under heavy load, the difference between them doesn't matter that much. And it's really just the OS is context switching back and forth because any one thread is not hot enough for it to basically stay pinned. But once you start to get hot, Netty really starts to take advantage of its architecture. And you can see that the Tomcat model hits the peak and plateaus at what it can do. So under light load, similar, this is where you start to cause less migrations, you improve the instructions per cycle, and the CPU usage per request with the CPU event loop architecture. So why was Netty faster for us in this case in Tomcat? So first of all, very clear, Netty just is better code in how much time it is spending on anything. Less object allocations, method invocations, all that stuff is better. The event loop architecture does reduce thread migrations, which affects cache warmth, memory locality, and instruction per cycle, which gets back to that original metric of how much CPU per cycle, which is actually what's affecting the throughput. And so, and then on the thread pool architecture, when we actually did flame graphs, like where you actually look at where all the time is going, we could see contention on the locks and the time that thread migrations were taking. So lots more details that we're not going into tonight. But what we determined is that with current JVM and Linux kernels, the event loops do have efficiency benefits. Now, take a different JVM, take a different Linux implementation, different threading implementation, nothing I just said would matter. But with the current generation of Linux and the JVM, these things actually do matter, and we can take advantage of that and architect accordingly. So what we also found is it was actually a lot simpler to get Netty to perform well, the event loop model, versus the Tomcat one, but it's certainly not easier. It's a harder programming model to do, but once you get it working, way simpler to scale the thing. I actually kind of think of it kind of like this. Tomcat and Netty, Tomcat's really easy to get started with, and then it becomes like that when you try and scale it in lots of different ways. Like the threading models are hell as you try and actually tune them as you put your systems under load. What I found with the Netty, like we spent 2 weeks tuning Tomcat. We spent about 15 minutes tuning Netty. Like there was like, how many threads do you want? And like the event loops. And we couldn't ever tune it any more than that. And so that was actually a big factor for me because operational complexity is a big deal in big systems. And how your system fails is a huge thing. So for us, we spend this enormous amount of time dealing with what the hell does our system do when you're passing the 80% CPU mark when we're scrambling to like scale up or something. Netty literally just like, yeah, whatever, I'll like speed up for you. It gets faster as you push into like 80, 90%, whereas Tomcat like falls to hell and like your whole system breaks. That was a big deal for us. So it does have benefits. So where are we going with this? And then I'm starting to finish off now. If you're getting concerned that I'm going to talk all night. This is the tail end now. So I'm going to take you into some of this is like if I worked at Oracle, this would be where I'd put up that legal slide of all these forward-looking statements mean nothing and you can't count on anything. So this is where we're trying to go with it. So we are actively adopting Netty in the edge systems, not the rest of Netflix. So if anyone ever asks you, they're not doing, the rest of Netflix is not. It's at the edge systems where we face the internet and we face the deluge of traffic coming in, where that's a much more important thing for us to deal with. We are actively adopting Netty right now. And this means the event loop architecture, non-blocking I/O. And right now it's still just HTTP. We're getting HTTP 1 working first. We will then be leveraging WebSockets, TCP maybe internally, and HTTP 2. So all those things are coming for us. We're actually experimenting with Aeron right now, which is a protocol and implementation by Martin Thompson and Todd Montgomery. It's actually built for like Chicago Mercantile Exchange and trading companies. This thing is bloody amazing. We can't even get close to this performance of this thing with Netty. And it's a protocol over UDP, so it's not TCP or anything like that. It's an own custom protocol over UDP. Event loops, non-blocking, and all that stuff. We're using it very surgically on one or two systems where throughput and latency is very, very important to us. Like we're talking like median latencies of 300 microseconds for 1 kilobyte responses, P99.9 of like 800 microseconds, very consistent. And that's in AWS networks, so we're not even controlling the networks. We can't get anywhere close to that with our other stuff. So we're pretty impressed with this so far and are pursuing it. Reactive Socket I/O, this is so new that I almost shouldn't be talking about it yet, but we are developing it completely in the open. So if you were to go there right now, you can see us doing all of our development right from the very first commit and like issue. We've been doing it in the open without ever announcing it. And a few people have like quietly found it and gotten involved with us. So lucky enough to be working with Todd Montgomery on this. Todd Montgomery is, he's done like protocols for like 20 years. So we're actually building our own network protocol for use over WebSockets and TCP and Aeron. And it's multiplex, duplex binary. It supports request response, streams with the reactive stream semantics, channels, bidirectional, and it uses the reactive stream flow control. So you can literally have the reactive stream publishers on either end, and it all just composes together over network boundaries. So it kind of looks like this. Reactive stream publishers on the left. Those are the semantics for, like these are what a client might look like. And our intent is to basically allow us to now finally have our network work with us instead of against us. Because networks are actually pretty good if you use them well, just we never actually use them all that well. If I turn this into RxJava types, it looks like that. So a single, which is like a future, except we didn't call it a future because this is lazy and futures are eager. So it's like an observable with only one item in it, and we can optimize it differently. The observables, and this is how I would summarize what Reactive Socket is for us. It's a formalization of the interaction models and the flow control needed for our applications, built in such a way that we can put it over multiple transport protocols, and so that we're formalizing it as an actual spec, and we will end up with a TCK so that we can have implementations in all the different languages. Right now we're working on Java and JavaScript. Someone has considered doing it in Go, and it's all just being done up on GitHub. Whether it ends up being successful or not, can't tell you yet, but our early signs of this are pretty positive. Just if you do go use the code, don't use it anywhere yet. That's the code that has all the race conditions in it I was telling you about this morning. But the protocol spec itself, I'd say, is like almost done. The spec itself really will only iterate at this point if we find things as we're building and using it. But we'd love to have your input if you want to actually come and get involved. And we did it because honestly we couldn't find any solutions over things like WebSockets that met all of our needs. And WebSockets, if you want to use it, it's got frames. And you have to invent something. And so instead of us just hacking at it with clever engineering, we decided to actually like legitimately define a protocol. And so we brought in an expert, got Todd Montgomery, who's got 20 years of protocol design experience. And he, like the first day working with him, he's like, yeah, here's the draft protocol. Like in his first day, I'm like, yeah, you earned your money. So RxJava 2 is under development now. And really it was just an idea up until about 3 weeks ago. Then another committer on the project, he's over in Hungary, David Karnock, he literally like ported all of RxJava 1 to 2 with reactive stream semantics in like 2.5 weeks. The guy's a machine. So we're in the phase now where we're basically going to spend many months just reviewing and iterating on API. And the reason why we did this is, first of all, there's some design changes that if I could go back in time 2 years with the understanding of using it in production and stuff like that, there's a few little tweaks that we would make that have prohibited like a few performance optimizations we could do. Like there was like some extra object allocations and things that just, we couldn't get rid of them without breaking the public API. This gives us a chance to do it. Java 8 and 9 instead of Java 6 and 7. Lots of goodness there, if for no other reason than our sanity, so we can write the code with lambdas and not want to rip our eyes out. We're adopting the reactive streams interfaces natively, and so observable actually implements the publisher, which means that like this code here, this handle request response that returns a publisher, I can just return an observable from it. And so basically the observable is just a concrete implementation of those types. So this was always our goal. The RxJava team was directly involved in creating the reactive stream spec, and but RxJava 1 was already baked. And so we supported the semantics, but you needed a bridge for the types. So now we're able to natively support the types, because we couldn't do that in V1 without a breaking change. And we're currently still debating a few decisions. We might take the observable type and split it into two, observable and flowable. We might let observable go back to being non-backpressured and be just purely push, because there are certain cases where that actually does model the world more accurately and where that's what you want, and you can optimize it differently because you don't have the overhead of the request end semantics and negotiation. And if we do that, we would call the backpressured type flowable. Basically, we're just, it took me a while to adjust to that name, but in Java 9, in JDK 9, the reactive streams publisher type is going to be, if it gets through the process, it'll be java-util concurrent.flow.publisher. And so they're calling it flow, so it will be flowable if that's what happens. Single and completable. Single is just a stream of 1. Completable is a stream of 0. And funny enough, actually, we find that we would really, really, really like to have that, because we use observable void all the time to represent something that will emit no data, but can complete or have an error. And we just want something that can compose. And so if we did that, we would actually support all possible, those 4 types with support for us, everything we need to do. RxJS, JavaScript side, is being rewritten from the ground up as well right now. Netflix and Google are working together on this, and it's all about performance and debuggability. RxJS 3 powers all of our stuff, all of our devices, but it just has some design decisions, again, made years ago that just kind of suck in retrospect. And this is like significant performance gains. The RxJava one is only in like the most, there's certain cases you can achieve it. Here, it's everything because of some fundamental things about how it works. And then the debuggability. So here's just a capture of the flame graphs in Chrome of the new and the old. And it dramatically simplifies the frames and what's going on. And I'm not going to walk through this right now, but a big part of it is it gets rid of trampolining when it's not needed and things like that, and makes it a lot easier to actually debug what's going on. So in closing, reactive programming can be incrementally applied. You can add it to your New York. You can make it work and get benefit from it. Mixed code bases are a challenge, though, and you have to just be aware of that coming into it. Concurrency via async service composition does work. And after using the more imperative style of concurrency and the function composition way, I will always now go to the composition way. And after 3 years of using it in production systems, I can confidently recommend it as a good solution. The RxJava schedulers and threads can be leveraged to help you bridge them, or like what we do, we actually don't do that. We just use Hystrix for that because it kills 2 birds with 1 stone. It takes care of our bulkheading and resilience and monitoring and metrics and all that stuff, while also giving us the concurrency around those blocking things. The truth, though, is that concurrency is still non-trivial, and RxJava does not trivialize that. It is a tool to help you provide abstractions and compose it, but you're still dealing with asynchrony and concurrency and all that entails. So it's not a silver bullet. We never pretend it is. And I do see people overutilize it, and I do see a lot of like, well, it's now like my hammer. I'm going to use everything with it. Just like any tool, it's just a tool. So hopefully this can help you pick a few pieces from this landscape and pull it back into your New York. Here's a lot of different resources. Reactive.x.io, if you just remember one thing, you can go there and find all that stuff. And I've talked a long time, but if you want to ask questions, I'll hang out as long as you want to talk at me. So thank you. Yeah.
So early on, you showed the example of talking to a database and making a synchronous database API
Yeah.
async. And you said that you showed an early version. You said you had got much better memory usage because used to be you were doing the whole query, done with the query, and then you had to like take all the results and accumulate them, right? But in the rewrite that you did, it seemed to me that you have just different resource usage in as much as you've kind of got pipelining. So as everything downstream is happening, you still have that database connection and that cursor and whatever resources are needed in the database for that particular query that's ongoing. Do you guys run into any issues with that kind of resources sticking around longer than you want, or also the query is open, right? So if there's any changes in the database, right, the transaction is kind of longer lived.
Yeah, so none of those longer lived things really matter because we're still talking about transaction times that are within what you want a user to be waiting for. So it's not like we have these things open for 20 seconds or something like that. The key thing is that instead of you allocating a chunk of memory, let's say for 100 items or 1,000 items or whatever, and then passing it along, you never actually allocate that. You literally just pass each item down the pipeline as it comes in. So all the resources for the database connection itself are all the same. It's whether you are accumulating it all as one or not. It's very similar to the difference in document or streaming style encoding and decoding. So if I receive a big like JSON or XML document or whatever, and I can do the document style where I just swallow the whole thing in, I do this huge decode or encode, this huge glob into memory, and I'm allocating and releasing these huge chunks, and you can see this affecting your system, versus the streaming parser where it just flows through it and you just do one element at a time. It's similar to that. But yeah, all of those concerns that you just brought up, yes, they would exist if you've got transactional issues and you're holding open connections a long time, all of those would apply. Does that answer the question?
Yeah.
Okay.
Did you look at Akka or Scala? My understanding, Akka might allow you to have concurrency at finer granularity than the thread. You could have many messages, many thousands of messages per thread. So your concurrency is much greater granularity, but you lose some type safety and so on.
So the question was, did we consider Akka or Scala? So I'll answer the Scala one first. 3 years ago, it wasn't even an option for us. We recently considered it as we were going down the greenfield rewrite, and we decided against it. We decided to stick with Java 8 for two reasons. One, the primary goal of this rewrite is to apply lessons learned and have a system that we can operate easily with the existing talent. And we basically all agreed that if we were to adopt a new language, that we would get 12 months into it and need to rewrite again. And so, and also we preferred the simplicity of just using the base platform, and we felt that Java 8 lambdas were, just the addition of lambdas was really all we felt we needed to use this programming model. So that's on the Scala question. On the Akka one, we have looked at it, we're aware of it. We have never been interested in pursuing it, primarily because in our environment, the primary gains that Akka are advertising for us is effectively the microservice type distribution. We don't need or want that. We already have a very sophisticated microservice architecture with discovery and resilience and scaling and all that stuff. And secondly, we have a real allergic reaction to with frameworks, honestly, that dictate how we write our systems. And so we have chosen to stick with libraries that I don't have to use them in different parts of the code just because. So those are the reasons why we've chosen what we've done. Roland and I have debated many hours about Akka versus other options. So we could talk about that offline if you're interested. You had a question right here, I think?
Go ahead.
Okay.
What do you think about fibers?
Fibers? I think fibers are fascinating, but only if the runtime natively supports them. We've explored Quasar, Pulsar, whatever it's called. We actually had its lead engineer, his name's escaping me right now, come to Netflix and present on it. I think it's a fascinating engineering effort that he was able to get anything like that to work on the JVM, but we're not going to go anywhere near that type of thing, just because it's not actually solving the problem. In fact, the evidence of that is that you can't use the fibers on the JVM unless it's using non-blocking I/O anyways, because they're not solving the blocking problem. So if that's the case, like if I already have to migrate everything over to non-blocking anyways, I might as well just use Rx, because it also doesn't solve the composition problem. So I think fibers are great as a better thread, but it doesn't solve composition. I still need a layer on top, like Rx or Akka streams or something like that for composition. It's interesting to me that in Java 10 and on, I finally started to see fibers show up as something that they're considering, but honestly, like, I'm not counting on it ever. I am interested in watching like what Go and them are doing. So I think fibers play a role if it can be done well. But I've never actually operated a system in production with it.
So my question is about creating like root observables. So like with Netty, there's stuff for HTTP and stuff like that already. But there seems to be a lot less documentation around like you've got a socket and data is coming across it. Like how would you get started creating an event stream of object or an observable based off of an event stream coming across a TCP socket or something like that?
So let me try and figure out, I didn't quite grok the question. So you're saying like, how do I create an observable from scratch with some data source?
Yeah.
And what's the premise of that question? Is it like the complexity of doing it right, or?
Like the correct way to approach it and those sorts of things. Because like Netty has an HTTP support already, so
Yep.
you've got some like Twitter firehose or something, right? Like
Yep.
It's just there. They've got a firehose. So if I wanted to do the same sort of thing to some server that's just got a socket that I connect to, like there's a bunch of stuff that's been done already. So where would I kind of?
So using Netty or using some other library? So basically the way you create observables is literally you observable.create, and it just gives you the observer and you just on next into it. And if you're okay with no back pressure, it's stupid easy. So if you don't care about the back pressure issue, you literally just on next until you're done and you complete. And pre-adding back pressure, that answer was sufficient and it was done. Post back pressure, it actually is not an okay answer I have found. And it's one of the things that we're currently working on in 1x and in 2x, which is adding the equivalent of generator functions that give the state machines for how to do something that supports back pressure, because it is honestly nearly humanly impossible to write back pressure, like raw back pressured observables without having a bug because of the concurrency and everything about it. And so if you're trying to do back pressured ones, come on and help us figure out the right, like we think we have it, but we're still in experimental mode, so that you have generators to do the state machine for you, because it's not easy. And this is actually the strongest argument for us splitting the observable and flowable type in two, so that they represent what they are, and if you don't need back pressure, just go use the easier type. I don't know if that answered the question.
It helps.
Okay.
Give me a little more context, the generator state machine. What is the purpose of that? What are the mechanisms?
So when you adopt the reactive streams model, where it's got the flow control built in, as soon as you've got flow control, that means you've got bidirectional communication happening on the stream, and you're only allowed to emit data when there's been capacity expressed to you. Well, what that means now is I've got state happening on both sides, and even worse, it can happen concurrently. So while I'm emitting, I can receive further interest telling me that I want more, and knowing how to actually, like wiring that up correctly so you don't have bugs and you're not emitting when you shouldn't be, or concurrently emitting or whatever, is actually really hard to do well.
So that's where the state machine.
Yeah, so that code I showed you with the JDBC one, that's the easy version of the state machine, because it's the synchronous model, where it just loops basically like on an iterable. And so if you're doing a synchronous iterable style reactive stream, it's pretty straightforward, and the state machine's pretty easy, because it's more like a scan operator. You could think of it like that. An async source is actually stupid hard to do manually. And think of an async back pressure source as paginating over like database results 10 at a time. And you say, I'm interested in 15 I'll stick with 10s. You request 10, 5, you're 5 of the way through that 10, and the next request for 10 comes in, and you're doing that so that you're going and fetching them while you're still consuming so that you're efficiently like flowing. And how do I kick these things off asynchronously, especially because now they can come back interleaved, and then make sure that they sequentially get concatenated back in and then flow with the correct flow control. It's not easy to implement from scratch. And so we think that we have an abstraction now that can become a proper state machine for that. And I'm hoping that that will get into the API within the next month. And we'll leave it experimental for a month or two. We annotate new APIs just so that we have the freedom to change them and harden that. I honestly think that that's the missing piece right now that has still made observable creation way too hard, because flow control is just hard. So that, hopefully that context helps. Yeah.
What is the other versions of Rx for other different languages? So clearly Netflix contains RxJava, but you have RxScala, RxConvia, and the list grows.
So the JVM ones all kind of originated out of our work in RxJava, and they're basically adapters on top of RxJava. Other folks, though, have started to maintain them, like Kotlin is maintained by Kotlin engineers. It has nothing to do with Netflix, for example. And they have all the commit and release privileges on that project, and Netflix has nothing to do with it. Outside of the JVM, you've got like Swift, Rx Swift for iOS is now a thing, and that's evolving. You've got Rx.net, obviously, the original one. That's all Microsoft. That has nothing to do with the GitHub repos that we have. Rx, they even have one for C++. Ruby has never really taken off, probably because Ruby's dying, but it's never really gone anywhere. And there's a few others in various stages of maturity. But you can basically, if you go to GitHub/ReactiveX, you can see them. Netflix is only involved in RxJava, the new RxJS. The previous one was all Microsoft, so the new RxJS, and we're working with the Microsoft contributors on that. And then RxGroovy, and we kickstarted Scala, but it ultimately was taken over by other Scala engineers in the community because we just don't use it enough to give it proper stewardship. So. Thanks, everyone.